Okay. Unfortunately, I didn't record what I did here, but I'm going to go over it kind of quickly. And this should reinforce it for everybody that's watching. If you have the y equals x squared graph here, and the table, you can construct the table for the inverse of the y equals x squared function just by reversing the columns. And we saw that earlier. If we do that and graph this inverse table, we get the blue curve that you see here. Let me make it blue, which is what it originally was. Okay, we get this blue curve. And that blue curve isn't a function. So I said, okay, the inverse of y equals x squared function is not a function because that blue curve isn't a function. It fails the vertical line test. And ultimately what that means, and the thing you really understand is, if you give me an x value, except for one, I'm going to get two y values, and you can't answer the question, what's the inverse function applied to this x value? You get two answers, okay? So we failed the vertical line test. There are two y values for most x values. So this is an inverse relation, not an inverse function. The blue graph is an inverse relation. To get an inverse function, we restrict x squared to a domain where it's 1 to 1. Because the reason this thing gives you two values of y for a given value of x is that this has two values of x that correspond to a given value of y. If this fails the horizontal line test, it's not 1 to 1, and this won't be a function. Okay, to make that happen, we can restrict the domain of this function so we only have this much of it, and that's 1 to 1. Okay, every x value has a y value, and every y value has exactly one x value. If we restrict this, then if we look at the table, we restrict the table to this much, meaning that we restrict the table of the inverse relation to this, and this gives us a function. We can graph those points, and then we can connect them or draw a smooth curve through the points. And right here, we have then our inverse function. Okay, fairly simple idea. And what did I do? Where did I do it? Okay. Now we do some algebra with this, but let's see. Now we can say, in general, that we can invert any one-to-one function, and the result's going to be a function. Because there's exactly one y value for every x value, exactly one x value for every y value on that curve, which you'll understand better if you've drawn a lot of these curves and answered a lot of the questions that have been there in the written assignments. Now, if the function isn't 1 to 1, what we do, restrict the domain so it is. Okay. Then we could get an inverse function. I can't tell how to read this board, so maybe I ought to do something to help you. Okay. So here we have the x cubed function, rough graph of the x cubed function. It kind of looks like that. And we know that if we reverse the columns, we're going to get a function that looks like this. And you really ought to go through all the basic functions, reverse the rows and columns, reverse the columns, and graph what you get. So you see, and you'll see that in every case, if you use equal scales for your x and y axis, your y equals x line is going to be at a 45-degree here, and this function is going to be a reflection through that line of this function. Each function will reflect through this line to give you the other. Okay, now, another example, and badly graphed, I apologize, but your basic square function is not 1 to 1. Here it is. It's here, and it's here. And seeing how to repair this, I might try to repair it. If you restrict this to the domain 1/2, 2, because the extended function is only defined between 1/2 and 2, then you get this red curve and you can invert it. Now, if I invert that a little more accurately than I did before, the inverse is going to go through the 0.11. They're going to look kind of like this. Okay, I haven't drawn that real well, but you can draw it yourself. You can see how they go. So now this inverts to something that looks a whole lot like it did before, but it's going to be different. And, graph the thing. It only takes a few minutes. Graph the thing, graph the inverse, make the tables. You only really need to make the tables for x greater than 0. You don't have to worry about this part because it's not going to be relevant to the inverse function. Now, we'll talk a little bit about the algebra and make sure we understand this. If your function is y equals f of x, this is your original function, then the inverse relation is going to be obtained by switching your y and your x, just like you did with the columns of the table. And you're going to get then you get your inverse function by solving this for y, and also restricting the domain of f of x if necessary. So, simple example, y equals x squared shows you most of the properties. Those are the reasons you do all these things. If you switch x and y, then your y is going to be written as x, your x's are going to be written as y's. So you're going to have x equals f of y equals y squared, okay? So that y squared equals x. Y squared equals x. We solve this for y because that's what you do. You solve for y. Now your domain is automatically going to restrict itself. So to solve for y, we take the 1/2 power of both sides, or the square root of both sides, but I talk about powers. Okay, I talk about exponents because radicals are actually more confusing, especially if you don't understand exponents really well. So I want to reinforce exponents because it's very important throughout the course. So you take the 1/2 power of both sides, and you note that this works only if you're taking the 1/2 power of a non-negative quantity. Okay? Because a number to the 1/2 times a number to the 1/2 has to be positive. Okay? So that the inverse function, it comes down to, you can do this as long as x is greater than or equal to 0. If you want to say that x to the 1/2 is negative, that you can do the 1/2 power of a negative number, but your number was originally negative, and that would say that the 1/2 power times 1/2 power is negative. You can't do it if x is negative. So x has to be greater than or equal to 0. Very important to note that restriction and write it down at every step after that. So we take the 1/2 power of both sides, which is the same as taking the square root of both sides. And y squared to the 1/2 is y to the 2 times 1/2. That's just y. And that equals x to the 1/2, and there's your inverse function. Okay, so y then equals f inverse of x is x to the 1/2, because solving for y and restricting the domain if needed gives you your inverse function. So there it is. So that f inverse of x is x to the 1/2, and x to the 1/2 can be written square root of x. Now to really convince you that f to the 1/2 means the same thing as the square root of x, if you square the square root of x, you get x, but only if x is greater than or equal to 0. Okay, if x was less than or equal to 0, then you'd be getting a negative here, but a square can't be negative. If you square x to the 1/2, well, your laws of exponents tell you that's x to the 1/2 times 2. Half of 2 is 1. That's x to the 1, which is x. okay? And again, this being a square, x has to be greater than or equal to 0. I didn't write it before, but I should. Since squaring this gives you x and squaring this gives you x, this must be the same as this. Okay. Well, that's an example. There are other examples, but you'll encounter them. And I believe My Open Math gives you a pretty good explanation of how you do such things. This is a process no matter what the function is. So make sure you understand you're doing this process. It'll help. And I'm afraid maybe I cut off some of the lower part of the board here. So just to reiterate, having solved this equation, to get y equals x to the 1/2, x greater than or equal to 0, solving for y gives us the inverse function. So we can say y equals f inverse of x is x to the 1/2. As long as x is greater than or equal to 0, there's your restricted domain. So we conclude that f inverse of x equals the square root of x, as long as x is greater than or equal to 0. And let's get down a little lower just in case the watermark gets you. Okay, now we want to talk a little bit about linear functions. I'm going to give you a quick synopsis of that, but it's stuff that I think should be pretty straightforward. Now, okay, now we want linear functions. We'll talk about linear functions, okay? Your basic linear function is y equals x. Vertically stretch it. You get y equals ax. Vertically shift. You get y equals ax plus k. Now, still a straight line. If x equals 0, y equals k. If y equals 0, ax plus k equals 0, because of course y equals 0 and y equals ax plus k, means ax plus k is going to be 0. So x equals negative k over a. So you don't have to go to all the trouble of shifting and moving points so many times further from the x-axis and everything, although you easily could. All you really need to do that for is 2 points, and then you get 2 points in the graph and you draw the straight line. But we could also use these intercepts. So y equals ax plus k corresponds to a straight line through the points zero k and negative k over a, 0. So your general graph will have the point 0k and negative k over a, 0. There it is. The y-intercept of that graph occurs for y equals k. And the slope and again, I'm writing down off the board there so we can't see it. Okay, again, here's the graph. Go through the point 0k, that's here. You go through the point negative k over a, 0, that'll be here. And maybe it's over here, it depends whether a is positive or negative. Also depends whether k is positive or negative. In this case, k is positive, which tells you that a has to be negative. You might think about that. Okay, the y-intercept occurs for y equals k. The x-intercept occurs for x equals negative k over a, just as I've drawn it. And the slope is the rise over the run. The rise is negative k. The run is negative k over a. And if you divide negative k by negative k over a, you get a. In any case, the slope is a. Okay. So this tells you what the equation of a linear function is, provided it doesn't go through the origin. Because k is 0, you have a problem with that, but still gives you pretty much a good picture. And we don't worry about that other, it'll work out here in a minute. Okay, so by transformations, left the letter out, so it's easy to insert an F. Transformation form there's your vertical shift and your vertical stretch. And I do it this way because you've been through transformations, and I presume you understand transformations. So you understand this. Whether you do or not, this comes from that transformation form. Okay. It all follows, and it's rather simple. Okay, now, If we use m for the slope, which is traditional, and b for the y-intercept, well, then m is going to replace a, because a is the slope up here. So you're going to write m instead of a. And you're going to write b instead of k, because k is the vertical shift, k is the y-intercept. Now, if the y-intercept is b, we're going to write b instead of k. Okay, now I assume that you're familiar with the slope-intercept form of the equation of a straight line. So you can get the equation of a straight line if you calculate its slope and know its y-intercept. If you have the coordinates of 2 points on the line, x1, y1, and x2, y2, then you can easily calculate the slope between those points. We did that earlier, third section of the book on rates of change, and we did it with slopes much earlier in the course. And I'm not going to go through the details of that. You should be able to do that, and I'll probably give you a written assignment where we reinforce this. But m is a slope, which is rise over run, which is y2 minus y1 over x2 minus x1. And a picture of that is easy enough. If this is x1, y1, and this is x2, y2, then we just do our fundamental triangle. And we see that the run is x2 minus x1. And the rise is y2 minus y1. So the slope is rise divided by run equals y2 minus y1 over x2 minus x1. And we put a box around that, as we did earlier. Okay, so that's it. We know that that's the slope. So the equation of the line is this. Can we determine B? Well, it's actually pretty easy to do with a fundamental triangle and slopes and stuff, but I'm not going to lay that on you right now. We'll just do it algebraically. If x equals x1 and y equals y1, then we can replace x with x1 and we replace y with y1. Okay. Well, if we know the 2 points, If we know y1, y2, and x1 and x2, that's an equation we can really easily solve for b. Well, I'm surprised that our educational system doesn't make people memorize this. Okay? That's not a formula you use. This illustrates a process. And the process is this. Example. If we want to get a line through the 0.53 and the 0.7 minus 4, your slope m is rise over run, which is -4 minus 3 over 7 minus 5, which is -7/2. So y equals -7/2 x plus b. Now we know that the 0.53, where y is 3 and x is 5, is on the line. So if y equals 3 and x equals 5, we're on the line. Then we get three equals -7/2 of 5 plus b. Write it big so you can see it way over here. So b equals 3 minus -7/2 times 5 equals 3 plus 35/2. And 3 is 6/2, so that equals 41/2. Or if you want it in decimals, it's 20.5. So the equation is y equals 20.5x, sorry, not 20.5x, -7/2 x plus 41/2, or y equals -3.5x plus 20.5. Meaning, go to the coordinate system and you take the 0.53 here, and then the 0.7, which would be about here, and then -5 would be down about here. So here's 5/3, and here's 7, -5, and here's your line. Now, what can you say about this line? Almost done here. Again, sorry to run over, had it glitched, Zoom took forever to come up, so we were several minutes late getting started. But we have 5/3 and 7, -5. It's a pretty steep graph, isn't it? And it's got a negative slope because it goes down as you go to the right. Well, a slope of -3.5 is a pretty steep slope, okay? So the picture is consistent with the slope of -3.5. The y-intercept is 20.5, meaning that if you extend this y-axis all the way up to 20.5, which would be up about here, and extend this line up until it hits that y-axis, it's very plausible that this is going to hit the y-axis when y equals 20.5. So that the picture that we get in the equation seemed to match quite well. Okay, so that's kind of it on